Algorithms require the best efficiency and absence of redundant statements to make your function as fast as possible and easy to read. Also, problems might have a few solutions, and there has to be a way to understand which one is the best in terms of efficiency. Here are two measures which are designed to evaluate it. Time complexity of an algorithm signifies the total time required by the program to run till its completion. Space complexity of an algorithm is the amount of memory space required to solve a given problem. Programmers usually call this calculation as function complexity or big O notation. What is the difference? Basically, it's the same thing. Let's say that big O notation is a set of shortcuts for a function's complexity terms. You will understand what I mean from the following examples. Function complexity considers a number of instructions you need to perform in order to solve the problem and get a desired output. I'll list all the types of complexity and its big O equivalents. Constant complexity, O of 1. Logarithmic complexity, O of log of n. Linear complexity, O of n. Linearithmic complexity, O of n of log of n. Quadratic complexity, O of n in power of 2. Cubic complexity, O of n in power of 3. Exponential complexity, O of 2 in power of n. And finally factorial, O of factorial of n. Do not be afraid of big O notations, you just need to memorize it first and then apply a bit of practice to feel what is what. Let's go through each one with examples to clarify the process of measuring. Constant complexity or O of 1. Here is an example of a function with a constant complexity. From this function, you can see that we have two operations of addition and division. You might want to say it has O of 2 time complexity, because we have two instructions, but it's not how it works. It will still be O of 1. As long as we have a constant number of instructions, we're gonna get constant complexity of 1. In terms of space complexity, we utilize only primitive variables, which means we have O of 1 space complexity. So far so good? We're moving to the next one. Logarithmic complexity or O of log of n. The most widely used algorithm that utilizes current complexity is binary search. Let's type an example function and discuss it in detail. We get an input as two variables, which are sorted array and target value we have to find in the array. Point out the binary search works only with sorted arrays. The main target of binary search is to reduce the area we're looking at. We take an array and define its start and end points. Our start point is 0 index and our end point is index 6. Range from 0 to 6 contains the whole thing of our array. We will use our start and end points to reduce the area that we are tracking. Now we have to determine what is the midpoint of the range. For the first iteration, our midpoint is 5, and we check if 5 equals to target 7. In our case, it's not, and we calculate that 7 is greater than 5. That means we have to check a limited area from value 5. Now our range indexes are from 4 to 6, and our midpoint is value 8. 8 is greater than 7. We move our index range and now it lies under index 4 and index 4, and the midpoint of that range is the same index 4 with a value of 7. Our check returns true, and we found the target value with just 3 iterations instead of brute force with 7 iterations. Finally, we have a better complexity than linear, which is called logarithmic, O of log of n, where n is the number of items in the given array. Space complexity of our solution is O of 1 because we use only primitive variables in our solution. If I already mentioned linear complexity, let's review it. Linear complexity, or O of n. This type of complexity is a lot easier to explain than the previous one. The best example of O of n complexity is going through all the elements of the given array. Here is an example of such an algorithm. We are given an array with numbers. The task is to calculate the sum of all numbers inside of the array. To do so, we have to iterate through all the elements of the array only once and implement one operation per iteration to increment our result value. This solution has O of n time complexity and O of 1 space complexity. As simple as that. Our next type is Linearithmic. Linearithmic complexity, or O of n log n. Method divide and conquer usually utilizes this type of complexity. It's worse than linear but better than quadratic complexity. If you are familiar with sort algorithms like quicksort and merge sort, then those will be the best representatives. Let's take a look at a merge sort. Point out that the algorithm has a helper function called merge, which is a good practice to separate code to logical pieces in case your function becomes bigger. That makes code more readable, and helper functions are always reusable. The main target of merge sort is to divide arrays using midpoint until you have only one element in each of them. Afterwards, the only thing left is to merge back all the arrays so they are sorted and get the only array as your output result. I strongly recommend you to write this algorithm in your IDE and try to run in debug mode with different input arrays to have a better understanding of how it works. The calculated time complexity of the algorithm is O of n log n. The space complexity is O of n, because we use helper arrays to accumulate results. You always need to remember, if you gain your time complexity, you sacrifice your space complexity, and the opposite statement works same. Next type is quadratic complexity. Quadratic complexity, or O of n in power of 2. You can take it as just nested loops. This occurs when we need to loop through the array for each item of the given array. As our example, we will use a very popular type of sorting, which is bubble sort. The idea behind bubble sort is that every pair of adjacent values is compared, and then the two values swap positions if the first value is greater than the second. This way, during each pass through the array, the largest value bubbles up to the top, and after each pass, the elements furthest to the right are in the correct order. This solution has O of n in power of 2 time complexity and O of 1 space complexity. The weirdest thing ever is that bubble sort is inefficient both for small and large inputs, which makes it completely useless practically, but the most asked theoretically. Strange, right? We're moving to the next type, cubic complexity, or O of n in power of 3. Let's say you want to find the solution for a multivariable equation. Then we can use such a naive solution which can be solved with a better efficiency, but I have to show you an example. Basically, we have got 3 nested loops, and it leads to a cubic complexity when in the worst case you will have n multiplied by n multiplied by n iterations to solve the problem. It has O of n in power of 3 runtime complexity. There is also a term polynomial complexity that works when you have an unlimited number of nested loops. It's denoted as O of n in power of c. You have to remember that you can always gain efficiency of the algorithm by using appropriate data structures and useful tricks. Meanwhile, we're jumping to the next type. Exponential, or O of 2 in power of n. Recursive version of calculating Fibonacci sequence. It looks fancy and it's easy to read, but we have got exponential complexity because we double our calculations each time the input grows. Finally, for comparison, the recursion method above will handle over 20 billion function calls and all of 2 in power of n complexity to get the value of the 50th element of the Fibonacci sequence, whereas a simple iterative method will make just 51 calls and all of n complexity to solve the problem. I mean, be careful with the method you choose for the algorithm, and let's review the last and the worst runtime case. Factorial, or all of factorial of n. Try to stay away from algorithms requiring this level of time complexity. Factorial is when you want to get a multiplication result of all the positive integers less than itself. For example, factorial of 5 equals 120, and we get it by multiplying 1 by 2 by 3 by 4 by 5. A factorial of 20 will give a result of over 2 quintillions, which is insanely bigger than factorial of 5. It grows astronomically. As an example of known problems that may take all of factorial of n complexity is finding all the permutations of a given string. In other words, to find all the variations of sequences of characters that can be generated from a given string. Finally, we're done with reviewing all the known types of function complexity. The last important thing I want to mention, all the algorithms have the worst, average and the best case of complexity, and you have to consider that when you choose the way you solve the problem. Depending on the most common input, you may choose different ways of implementation. Hope this video was useful for you. I recommend you to learn data structures before you dive into algorithms. It will help you a lot to gain efficiency of your solutions. Subscribe to this channel to get reviews of widely used algorithms. Bye bye and have a good startup.